At 320 kilometers per hour, a high-speed train is moving with such extreme velocity that it covers nearly 90 meters every single second. For over a century, railways have relied on a simple foundation: ballast. These crushed stones sit beneath the tracks, providing drainage and distributing the immense weight of the train. But when you push past 250 kilometers per hour, the physics of that track environment completely break down. The sheer speed of the carriages creates massive aerodynamic suction, while the wheels send extreme vibrations deep into the ground. A low-pressure vacuum forms beneath the fast-moving train, literally sucking loose crushed stones out of the track bed. These high-speed projectiles ricochet, severely damaging the undercarriage and permanently displacing the track's alignment. At these speeds, millimeter deviations can cause fatal derailments. To safely manage these forces, engineers are installing the Japanese J-slab ballastless track system. This completely eliminates the loose stones, replacing them with highly precise precast concrete panels that act as a rigid, permanent foundation, cushioned by a specialized shock-absorbing mortar. This solves the physics problem, but it creates an engineering one. To survive 320 kilometers per hour, you need a 500-kilometer elevated corridor made of millimeter-perfect concrete. Building that using traditional methods would take decades. This enormous elevated corridor is currently stretching across the landscape of Western India. Traditional elevated rail lines are built segment by segment. Small blocks of concrete are hoisted high into the air and slowly tensioned together, a process that is highly vulnerable to weather and extremely time-consuming. To bypass this delay, the project utilizes the full-span launching method, or FSLM. Instead of building the bridge mid-air, construction is shifted to massive ground-level casting yards. Here, entire 40-meter-long concrete bridge spans are poured and cast as single, solid, monolithic pieces. Each one weighs 1,000 metric tons. This split screen illustrates the efficiency. The top shows traditional methods taking days per span, while the bottom shows FSLM in action. Giant carriers transport the 1,000-ton block, and a specialized gantry places the entire section onto pillars in roughly 16 hours. By turning infrastructure into a mobile assembly line, engineers can lay track 10 times faster. But these massive machines hit their limits when severe physical obstacles block the path. One of those obstacles is the Ahmedabad-Vadodara railway line. The bullet train viaduct has to cross directly over active Indian railway tracks without stopping the dozens of passenger and freight trains passing below. To clear this span, engineers executed a monumental heavy lifting operation. Using a massive 2,200-ton crawler crane, they hoisted a 1,360 metric ton concrete beam 15 meters into the air, locking it into place in under 4 hours. While cranes dominate the sky, an entirely different class of machinery is required underground, specifically for the 7-kilometer undersea tunnel beneath Thane Creek. When a train enters a standard tunnel at high speeds, it pushes a massive column of air ahead of it. In a tight space, this creates dangerous high-pressure waves that can physically damage the train carriages and the tunnel walls. This cross-section details the solution. A standard 6-meter metro tunnel violently compresses that air. To dissipate pressure, engineers use India's largest-ever tunnel boring machines, measuring over 13 meters wide. They grind a single, extra-wide tube for both tracks side by side, allowing aerodynamic forces to safely disperse. Whether hovering thousands of tons over active railways or carving oversized tubes beneath the seafloor, the construction equipment has to perfectly match the extreme physical realities of high-speed transit. All of this massive engineering ultimately addresses a very familiar problem for the daily passenger: the chronic waitlist culture of the Indian rail system. This diagram illustrates the root cause of that bottleneck. Right now, legacy tracks are forced to share slow, heavy freight, regional trains, and fast express trains. When vastly different speeds share the exact same physical rails, the overall throughput of the network is mathematically constrained by the slowest trains. By building a dedicated high-capacity pipeline for premium intercity passenger traffic, those fast trains jump over to the new corridor. This unloads the legacy network, freeing up massive amounts of uninterrupted time blocks for standard passenger services and heavy freight to flow freely. And the technology running on these new dedicated lines is moving toward domestic control. Japan provided the initial hardware, but India is actively transitioning to manufacture its own high-speed rolling stock. A domestic consortium is currently manufacturing India's first fully indigenous high-speed train sets. Designed for operational speeds of 250 kilometers per hour, the first 8 coach prototypes are slated to roll out for extensive testing by late 2026. This deployment of unprecedented machinery physically carves out the national breathing room.